Okay. Hello, everyone. Thank you very much for that nice introduction. Let me try if I can turn those things off. Is there a way to... Well, we'll live with that for now. Okay. So I've always been really fascinated by the intelligence of animals. And I want to show you this video of a crow. And this is a crow that's trying to get the food in the center tube here. Um, and what the crow is doing is it's doing these science experiments in order to figure out how can I get the food. Unknown to the crow is that the red tube on the right is actually connected in the bottom blocks with that tube in the center. And what the crow starts to do is starts to build a causal model of what happens inside this environment. And it figures out that if I put rocks in the red tube, that's going to cause the water level to go up, right? And make it easier to get the food. But if I put rocks in the blue tube, right, it learns very quickly that's not going to help it achieve its goal in order to get the food. And so I find this kind of incredible because this is a really small brain, right? That is building up this 3D world model. It's causal about the world in order to accomplish its goal. The same Crow lab that experimented with this, they actually had a bunch of kids come in and try to do the same task. And when little kids just spend all their time trying to jam their fingers into the tube in order to grab the food, and they could never get the the food. So before I get too far into this, I want to say that I really like LLMs and all the things that they can do, and I think that's a really interesting research direction to be exploring. But I do want to compare and contrast what LLMs are doing versus these crows, right? In order to get a lot of generative models and AI systems to work well, you need a ton of power, right? And these crows are just eating worms for breakfast, right? The amount of calories that they need in order to perform these skills, in order to learn these tasks, they're very efficient, right? And that's something I think is a really key challenge for this field going forward, just computer vision, AI in general, is this issue of efficiency. We don't have anything that's close to the efficiency of natural brains. Crows have to live in this world, and same with us. We live in this world where our actions and everything we do actually has consequences, right? LLMs and generative AI, they can hallucinate all they want. There's no consequence to them, right? So how do you build these systems, and especially for robotics, right, where you face and you deal with these types of consequences? And a lot of animals, every animal, we learn from our surroundings, right? We're self-supervised, right? We get feedback from our environment, right? That's the example of the video I just showed you is the example of few shot learning. Just from a few shots, they actually can build a model of what happens inside that inside that world. So today I'm going to talk about a couple different projects we've been exploring kind of inside this space. And one project that we've been exploring to get our feet wet with this is trying to build a system that can actually build up a model and actually build different tools inside of its environment. So if it can build up a world model of how a particular object works inside this environment, you should be able to use that in order to solve different tasks. And so we started this with this really fun problem that I think hopefully everyone in the room has probably tried to do this at one point, is how do you actually optimally fold a paper airplane, right? There's many different ways. You can all grab a piece of paper and start folding in different ways and throw it, and you can watch and see what happens. How can we build a robot system that actually can perform these same types of tasks and actually, through experimentation with the world, figure out what's the best way to actually design a paper airplane and throw it to? So we built this contraption. Printer prints out a piece of paper. These robot arms can pick it up, fold it in different ways. We cheat a little bit, and we can stick on a handle there to throw it, and the robot arm pulls back, and it's going to throw it forward. And here's what happens. not that great, right? This is the very first design that it came up with. But we can mount these cameras and these on the ceiling here in order to watch how far does that plane actually go. And this can create a feedback loop, right, for the system to figure out how should I actually fold this piece, how should a system fold this piece of paper in order to get the airplane to go as far as it can. And so we built a system here that basically does this over many hours. It just prints out paper, folds it, throws it, and tries it, and refines this design over and over again in order to figure out what is the best paper airplane for doing this task. So the question that we have to solve is, given a piece of paper, where should you put these folds in order to maximize the distance that it's going to travel? Sorry, it sounds like lunch is being made right behind me. It's I'm starting to get hungry. That's fine. Okay, so we built this approach where it would take a particular design, it would build it, it would throw it, and then watch it. And we want to solve the problem, what is the best fold, right? How can I invert this process in order to figure out what is the fold that's going to maximize the distance that it's going to go? So I'll skip a lot of the details here, but we basically built this predictive model that learns, given a particular design, it predicts how far that particular design is going to go. And what's nice about this is that this is differentiable. So you can use this as a surrogate and basically use propagation to invert that model and learn and actually figure out what is the best design that is going to maximize this distance. And so you have to do both these steps in tandem, where you are doing these experiments to figure out, how good is this particular design, training that predictive model at the same time, and doing an inversion of that in order to figure out what the next best design is. So, once you do one step with this, it starts to build a slightly stronger design here. And over time, it starts to optimize this design more and more and more. This is just after about an hour of doing experimentation here. And finally, it converges on this great design that actually goes really, really far inside the lab space here. And I'm putting the design here on the top right. And one thing you might notice a little odd about this design is that this design is not symmetric, right? Probably our priors here would be that the best design for an airplane would actually be symmetric, but actually figured out something that to go further, it actually should not be symmetric. And what we didn't realize all throughout doing this project was that there's actually an AC vent at the very top blowing cold air the entire time. So it actually optimized the design that turns the plane into the AC vent in order to go a little bit further. Okay, so this is a really fun project. This is our first project in robotics we start or to do. And here's just the system would basically learn over time and the evolution of the designs it would build, where it gradually build these airplane designs that could go further and further away. And I think what's I find really cool about this is that this is a system that is learning purely in the physical world. There's no language, there's no internet here, no foundation models, right? This is just a system learning purely from the visual feedback, right? So this is not just, this project wasn't really just all fun and games. There actually are practical uses for this. And one of the other designs that we explored was building what's called the Kirigami gripper. So rather than folding paper, this is a way of cutting paper in order to build tools. And so what a Kirigami gripper is shown on here is if you apply cuts to the paper in just right spot and then you apply force, what that does is it builds this type of gripper that can pick up objects. So we did not invent the concept of Kirigami grippers. The original work that looked at Kirigami grippers, they tried to tried to build a first principles approach to model paper, and then use that in order to figure out what the right way of designing these grippers are. These are potentially useful in health applications because this is disposable, right? After you build this gripper, you can throw it away and build a new one for the next first person. Um, so we built a similar type of approach, applied the same method that we did for the paper airplane, but rather than throwing it, it would actually try to grip things. And it could figure out without this is just from learning here. It actually could figure out how to cut the paper in just the right way so that I can pick up all different types of objects. And so here's just some of the types of things I was able to pick up. It actually can it actually built a design that could apply enough force to pick up 3 strawberries at the same time. So here's kind of a more visualization of all different things that it could do, and it would build these designs that got better and better over time. So at the very beginning, when it knows nothing about paper, right, it built these really bad designs where it couldn't do much. And over time, it actually figured out how to apply these cuts in just the right way to pick up a lot of different objects. Okay, so one of the, I think, main challenges in robotics, there's actually a lot of different challenges in robotics, but one of the main ones is generalization. And how do you build these systems that can basically generalize to totally new scenarios that's not seen in training? This is, in computer vision and NLP, maybe we've gotten a good handle on this, which is go train from the internet, right? And we basically see everything and don't have to solve all generalization. In robotics, it's not as easy, right? Because it requires a lot of actual data that you got to collect in the physical world. So data is very expensive to collect. But really, this goal, I think, is an interesting challenge here is that can you build these robot systems that maybe train on some objects, and there's some big distribution shift that happens at test time, and can it adapt to that? This being a particularly extreme example here. So the size of the data is one of the key issues here. The amount of visual data that we have, you can get from the internet, from videos, is just massive. And if you want to collect data in the real world, it's very expensive, right? I mean, even if you do whatever approach you want to apply, whether it's reinforcement learning or some sort of behavior cloning, the cost of getting that data is massive. We've been exploring this approach where we want to use generative models, particularly video models, as a backbone for a policy. And there's these models have gotten extremely good. Some of the previous talks we saw in this workshop actually have been talking about this. And they model so much of what happens inside of our world that if we can somehow use them for a policy, we potentially can get systems that generalize to new situations much more efficiently. So we've been exploring this in a line of papers, and we built this system that the way it works is given a particular scene, it uses a video generative model to first imagine what a person would do in that scene. So if the task was to do scooping and scoop the rice into the bowl here, the video generative model can imagine, actually generate, here's what it would look like for a person to do that. And then have a robot imitate that in the physical world. So I can play it again. So where's the generation from this model, saying this is not a real hand, right? This is Gen AI making up a hand and a spoon, right, doing this task. And then we can actually track that spoon and use that to control a robot to perform that task. So this is an approach where basically you're doing, behavior generation via video generation. And the hypothesis here is that the video generator has seen so many situations that we should get good generalization to new things even if we've never collected physical examples of that. So in the first version of this work, here's one example that I think is illustrated here. This is a simple task where you have to push these foam numbers into a particular goal spot, and so the transparent object is the goal spot being shown there. And this is what behavior cloning does if you don't have access to the internet, right? You just train this policy on numbers 1 through 1, 2, 3, 4, 5, and then you start testing it on 6, 7, 8, 9, 10, right? It actually can't do it. It's actually really hard for it to figure out how to push this. Here's the same approach with this, where you've had this model that generates a video of a person doing it, and then you have a robot actually imitate that. And it can actually perform this task pretty well, even though it's never seen a number 7 before, right? It's trained just on 1, 2, 3, 4, 5. Now you're testing it on 7. So this is one of the first versions of this work that we produced, and this was appeared at Coral last year. We've now been working on a version 2 to basically extend this and make it work much more well in a lot of different situations. And we basically moved to this system that does this from a wrist camera instead. So, to talk about drawers, right? If you want to try to build a robot system that can open the drawer, what we did is, rather than having the video model predict from a top-down view, it's actually going to be predicting from an egocentric view where the camera is on the hand, right? And it's going to be generating a video of what that egocentric camera would look like as you perform different tasks. So this is a new paper that is so fresh it's not even on arXiv yet. So this was it's in submission to a conference and will be on arXiv soon. And so basically, in David's talk, there was just, and I guess he was talking about Noah's statement too, about how maybe the best priors for 3D are actually in these models for video generation. We also think something similar for robotics, that a lot of the knowledge for solving these tasks are actually inside these models as well. To extract that type of knowledge from these approaches, we basically have to solve a structure for motion tasks now, right? If we're generating these videos of the camera moving around, the way you control the robot is to track the motion of that camera, right? And then have the robot perform these same tasks. So we experimented with a bunch of different structure motion techniques. It's actually pretty hard to get structure motion to work in these cases, just because classic issues where there's a wall, there's not many features there. We actually were able to show that we could basically train a transformer basically to perform that task. And then we fine-tune the model for video generation on about 300 examples, right? This is very small, right? The generative model here has been trained on billions of examples, right, from the web, and we want to basically align it to this task that we care about, and so we fine-tune it with about 300 different human demonstrations on a couple of different tasks. And so what we found was that this could generalize to situations that is not seen in training, right? And so to explain this slide, this is a task of trying to open a drawer that's never seen before. I'll play the video again in a moment. The top row is the rollout in the physical world. This is the robot actually performing it in the actual world here. The bottom row is the prediction from the model, the generative model predicting what would happen. So the video prediction is pretty good, right? It's almost like hard to tell the difference. I'll play this again. And so the video model at the bottom was predicting how should the robot move, right, in order to open this drawer. And so it predicts 3 different camera views. We found that helped. It predicts both the egocentric view on the far right, as well as two different camera views. So it generates that plan first in pixel space, right? And then a robot actually then retract that camera pose and actually perform that task in the actual world here. You can see some examples where the video generator model gets it wrong. As the drawer opens, it can't possibly know what's inside of the drawer. So it first gets it wrong, right? And then once as it sees more, it actually can revise its prediction. Here's it working on novel objects. This is for trying to upright objects. These are objects that have fallen over. It's never seen this object before fall over. And the task is actually to control the robot to pick it up and put it into the upright position. So I can play that one more time. Okay. And so, yeah, it works on quite a lot of different tasks. And so the key point here is that the video generator is actually doing most of the work. So it's actually controlling the robot in terms of how to do this planning. And so the generalization capabilities that you get are basically coming from that because it is able to generate videos that are such high quality and it's seen so many different examples on the internet. It can generalize these cases where you maybe only have a small number of demonstrations in the actual world. We benchmarked this. We did all this in the real world. In simulation, we actually then benchmarked this on a lot of different tasks. Found some pretty interesting results actually. So it actually on one of these benchmarks actually got state-of-the-art performance, beating a lot of behavior cloning approaches. But what I found most interesting was it actually can generalize to these tasks that you've actually had no supervision for. So I don't want to use the word zero shot quite yet. I think this is not able to do zero shot to all different types of tasks yet. But it's I think it's actually a very nice step towards that. So this is a bar chart showing success rate for lots of different tasks inside this SEM. The bars on the left side with the gray background, those are tasks that's seen in training. And the bars on the right are tasks that's not seen in training. These are completely new tasks that's never seen before in the training. And the blue bars, our chart is our model, and the orange is basically a behavior cloning based baseline, right? So behavior cloning basically does not work almost at all when you want to generalize to these new tasks that you've not seen, right? But when you have access to this policy is trained on video in the first place, you start to get that. So anyways, we're very excited about very excited about this. It doesn't always work. Like sometimes they'll hallucinate a bunch of hands, basically being able to solve the problems. Obviously, there's no way for a robot to go do that. So there's still lots of interesting times to be exploring this. So happy to take questions. Thank you.
Any questions from the audience? So I actually have a question, so I'll start. So you actually show some successful cases and failure cases of the video generator model, and some of the cases you can call them successful because it can enable the robotics to really manipulate, but still it has some artifacts because when you pull it doesn't actually pull anything. It just hang there and then do the action. So what do you think is the boundary of the generative videos and the real physical world, and if there is a really gap between the real physics and the
fantastic question. So I actually I don't want to talk about this, but one thing I'm interested in this project is that robotics is a way of evaluating what generative models do, right? Like so video generation produces really cool videos. You like watching it. How do you actually evaluate whether that's a good generation or not, right? Pleasing to our eyes, but is it true, right? So in some ways, robotics is a way of doing evaluation. If you can generate videos well enough, right, that you can actually then translate that to a robot, that's one way of saying that the video generated is strong. Now, there are lots of examples where the system will fail. It has 3 hands come in. There's another type of failure that I call the Donald Trump effect, where it basically, it hallucinates success, you know what I mean? So it, you know what I mean? It's supposed to pick something up, it can't do it, so it just hallucinates it that it did the right thing, right? There's also this, you know, I think another, but maybe the most important issue here in some ways is that this is purely visual. So you're missing touch here, right? So I think that's actually really important to really make this work in a lot of different cases. Touch needs to be handled here. Yeah.
This failure with the multiple hands, is that just a matter of constraining the prompts properly, saying if you were a robot with 2 hands, how would you do it? Would that solve it, or?
Yeah, good question. We didn't really, this only happened a couple times, so we didn't explore this too much. We did find that so we basically fine-tune the model with some demonstrations. I think this goes away as you fine-tune for more and more. We just need more compute.
Okay, so if there's no further question, let's
Thank
thank
you.
Professor Carl.